So what we're going to be talking about are trees. Um, and we're going to start with just going through some terminology about trees. Um, so here's a picture of a tree. Um, you can see up here the points in a tree can be called nodes or vertices. We're usually going to use the word node. So in this picture here, we would have nodes A, B, C, D, E, and F. And then the connectors between the nodes are called edges. Um, and then basically we're going to look at this the way we would look at a family tree, right? If you are familiar with a family tree, you could see in this picture that A is probably the grandparent of D, E, and F, right? B and C are the children of A. B and C are siblings. C would be D's uncle, and so on. And we're going to use a lot of that same family tree terminology when we're talking about trees. So you'll see we use the word parent, child, sibling. Oldest child or first child would be the leftmost child. So D would be the oldest child or leftmost child of B. Any questions about any of that so far? Pretty straightforward, I think. The only weird part might be just thinking about what on earth this could possibly have to do with computer programming, but we will get there in a minute. So we use kind of a mixed metaphor here a little bit. And sometimes we talk about these structures using family tree terminology. Sometimes we talk about them using actual tree terminology. So the word root would mean A is the root of this tree. And so when we're talking about comparing these pictures to real trees, they're sort of upside down trees, right? So the root is at the top, that's A. Leaves in a tree are nodes that don't have any children. So the leaves in this tree would be C, D, E, and F. You can use the word ancestor and descendant just the same way you would use those words in a family tree. Okay, so you can use the word subtree. So this tree right here that has B as its root would be a subtree. Of the tree whose root is A. So hopefully that makes sense. And then you could also, even just this node here, D all by itself is a subtree of the tree A. It has one node in it. I'm looking for the bold text here to see what we need to talk about. We're not going to worry about that. Okay, kinds of trees. General tree means that any node in the tree can have as many children as you want it to have. So all of the trees we've been talking about so far are general trees. We are actually not going to talk very much about general trees. We're going to be talking about more specific kinds of trees because they tend to be a lot more useful in computer science than just a general tree. Not that a general tree is never useful, but not as often. Okay, binary tree. What we're going to be talking about in this class is a more specific kind of tree called a binary tree. A binary tree is simply a tree where every node has two or fewer children. Okay, so just like a regular tree, except you just limit the number of children that each node can have. Let's see, 219. I'm looking for figure 15.2b. Okay, so here's a binary tree, right? Because every node has 2 or fewer children. So if you have a binary tree, you can talk about each node is going to have a left subtree and a right subtree. Right, so looking here, this whole tree, the left subtree of the node Bart is this tree here that has the root Homer. And the right subtree of this node Bart is this tree that has the root Marge. So left subtree and right subtree. Okay. One big example of how trees are used is algebraic expressions. So here are some pictures of some binary trees that represent algebraic expressions. We use binary trees for this because the vast majority of our operators are binary, right? Some are unary, one is ternary. So each operator is going to have 2 children. Each of those children is going to be either an operand. Well, each of those children is going to be an operand. So this minus's left operand is A, minus's right operand is B. But those operands themselves could be expressions, right? So in this expression, we've got minus, the left operand of minus is A. The right operand of minus is B divided by C, the whole expression, right? Any questions about the relationship between these binary trees and the expressions that they represent? That makes sense what's going on there? Using the pause to get my participants list out here and see who's actually here. Just out of curiosity. Okay, I will take that to mean that things are going okay so far. Okay, so we started talking about general trees, and then we started talking about binary trees. Now we're going to take it even, drill down a step further and talk about an even more specific kind of tree called a binary search tree. And a binary search tree is just a special kind of binary tree whose nodes are in a required order, okay? So the requirement for a binary tree to be considered a binary search tree is that for every node in the tree, all of the values less than that node are in its left subtree, and all of the values greater than that node are in its right subtree. So probably the best thing to do at this point would be to show a picture. Okay, so here's a binary search tree. The way that we would verify that this is a binary search tree is we say, okay, let's look at Jane. Is it true that every node in Jane's left subtree is less than Jane? Yes, that seems to be the case. Is it true that every node in Jane's right subtree is greater than Jane? Yes, that appears to be the case. But we're not done yet. We need to do that for every single node in the tree if we really want to confirm it, right? So we have to look at Bob and make sure that every node in Bob's left subtree is less than Bob. Every node in Bob's right subtree is greater than Bob. And then same thing for Tom, okay? So what that does for us, just to kind of give you a sneak preview, is if I am looking for a particular name in this tree, and I I see that the root of the tree is Jane. And let's say I'm looking for the name Peter, right? I see that the root in this tree is Jane. That means I can immediately ignore everything in Jane's left subtree and just look in Jane's right subtree for the name Peter. Okay. And then so on, right? I get to the name Tom. I realize that Peter comes before Tom, so I can ignore everything in Tom's right subtree, and I know that Peter, if it's in the tree, is going to be somewhere in Tom's left subtree, and so on. Okay. All right, the height of trees. This is something that it's easy to get off by one. So let's just take a careful look at it, okay? The height of a tree is the number of nodes on the longest path from the root to a leaf. So here are some examples. Okay, in picture A, how many nodes are there on the longest path from a leaf to the root?
3.
3, right? In fact, pretty much every path from a leaf to the root has 3 nodes on it. So the height of this tree is 3. You can imagine that that's a little bit arbitrary. It could, computer scientists could have decided to define the height to be the number of edges on the path between G and between a leaf and a root, but we're going with nodes. What about B? What is the height of tree B?
5.
That's correct, 5. What about C? Someone else. What's the height of tree C? I guess this is, I'm thinking it's probably safe to assume that you got the idea here, right? But just one more.
Yeah.
So what's the height of this tree here in part C?
7.
7, right. Okay, I think that's pretty straightforward. The only tricky part is just remembering that it's the number of nodes on the path, not the number of edges on the path. Looks like they're talking about, okay, so I guess we should just talk about what we mean when we say the level of a node n. Basically, we just mean that we consider the root to be at level 1, and then every time we go down to a child, we add 1 to the level, right? So I think that's pretty straightforward, and I'm not sure we're actually going to need that again. So, all right, still just working on some terminology here. I think we're almost done with terminology, but now we want to talk about full, complete, and balanced binary trees. I'll be honest with you, every time I do this, I have to look up to see what's the definition of full and what's the definition of complete, because I get them confused with each other. But let's see, a full binary tree, in a full binary tree, all nodes have 2 children each. So a full binary tree has as many leaves as possible. Okay, so basically what I'm trying to do here is read the formal definition and then give you a more informal, intuitive way of thinking about it. But it just means that you can't add any more nodes to the tree without adding another level, right? I think that's probably the simplest way of saying it. Questions about what a full binary tree is? Okay. The complete binary tree, the requirements are not quite as restrictive, okay? It just means that, so here's a complete binary tree. It just means that all of the levels except for the bottom level are full, and the bottom level has been filled up from left to right, okay? So you can almost just look at the picture and have me just shut up for a second and understand what a complete binary tree means. Any questions about what a full binary tree is and what a complete binary tree is? I'll just tell you that one of the reasons why those terms are important is that binary trees become pretty useless if they get out of balance. So in order to have a really good binary tree algorithm, the binary tree algorithm has to have some sort of mechanism for making sure that the tree doesn't get too far out of balance. So that's why we're going to be talking about full binary trees, complete binary trees, and balanced binary trees. Where did balanced go? Okay, so here, a binary tree is balanced if the height of any node's right subtree differs from the height of the node's left tree by no more than 1. Okay, so that's a pretty technical definition, and we're probably just going to have to go with that sort of formal definition. And if I ask you, if I give you a tree and I say, is this binary tree balanced? I think you're basically just going to have to apply the definition, right? Look at every node in the tree, find the height of that node's right subtree and that node's left subtree, and make sure that they differ by no more than 1. Okay? Binary trees in figures 15.7 and 15.5a are balanced. 15.7. You want to go back and look at that? Here's 15.7. This is balanced, right? Because if I take any node in this tree, its left subtree is going to have either the same height as its left subtree, or they're going to be off by 1. So that makes it a balanced tree. So 15.5, obviously A is balanced, right? In fact, every subtree in the whole tree has the same height as its sibling subtree. A, C, and D are not balanced. They're way out of balance, right? For example, in C, A's left subtree has a height of what? 0, right? A's left subtree has a height of 0. Feel free to stop me if that's not clear. I'm kind of assuming the reason no one answered is just because you're bashful or tired, one or the other. What is the height of A's right subtree? 1, 2, 3, 4, 5, 6, right? So obviously the heights of A's left subtree and right subtree differ by more than 1. Okay, so Kaylin has pointed out another way you can check to see if a tree is balanced or not. Look at every leaf in the tree, find the height of every leaf in the tree, and they should differ by no more than 1. I'd have to think about that. I mean, intuitively that sounds right. But it's not foolproof. Okay. I'm kind of thinking to myself, yeah. Anyway, we know the formal definition. We'll go with that for now. Okay, the maximum and minimum heights of a binary tree just means given a certain number of nodes, what's the tree with the smallest height you can create, and what's the tree with the largest height that you can create, right? So the maximum height of an n-node binary tree is obviously n, right? Because you just line the nodes up all, for example, line them all up going off to the left. And that would be the maximum height. The minimum height is going to be a complete binary tree, right? All right, I'm not too worried about that little piece of terminology. We'll go with that for now. The result is kind of interesting, and I'm kind of hoping that by now, just to give yourself a little test, if you've understood some of our discussions this semester, particularly about big O analysis, and I ask you, okay, if there are n nodes, what is the minimum height of the tree going to be? Well, you can see that I'm going to want to fill the tree up as much as possible, right? So we could make a little chart. I hope this isn't like, I hope you're not rolling your eyes going, oh man, I'm having this conversation again. But this is just so important, and a lot of students don't really get it. So I'm gonna just do it again. So if I have one, let me make that a little bigger. Oh, I just realized you can't see what I'm doing. Hold on. I guess I will just share my desktop. All right, so I'm just leaving these pictures up over here so as a reference in case we want to look at them, but just thinking, if I have, I'm going to just start right at the beginning. If I have 0 nodes in my binary tree, what's the minimum height of that binary tree? Right, it's, obviously it's going to be 0, right? Okay, if I have 1 node in my binary tree, the minimum height, I think obviously is going to be 1, right? If I have 2 nodes in my tree, the minimum height is going to be 2. That would be like this picture in part A, except without the bottom node. If I have 3 nodes, the minimum height is still going to be 2, right? Because I can have a picture like in B, except without this bottom node. If the number of nodes is 4, then the minimum height is, is like in part B here, right? This is a tree of minimum height with 4 nodes. So the height of that tree is 3. 5 nodes, looks like that's C, right? Yeah, as a matter of fact, that's what they're doing. They're just adding 1 node at a time. So still 3. Then 6 nodes is like D, so still height of 3. 7 nodes is like part E, so still height of 3. And then when I turn to 8, I'm going to have to add another level, right? So that's going to go up to 4. Okay. All right. Anyone want to predict how many nodes I'm going to need in order to make the height go up to 5?
8.
I'm sorry?
8.
Sorry, you're cutting out.
Said 8.
Well, so 8 nodes makes the height required. Let me try that again. 8 nodes is where the minimum height becomes 4, right? So if I want, now that I have a minimum height, and now that I have a height of 4, that would be like adding one more node on the left here to E, right? And then if I've got 9 nodes, I'm going to add another node to the right of that node. And then with 10 nodes, I'm going to have a left node over here. 11 nodes, I'm going to have a right node here. 12 nodes. Oh, eight more. Okay, yes, that does make sense. Okay, so, right. To fill up my 4th level here, I'm going to need 8 nodes, right? So that's going to be a total of 15. So bottom line there is, when I've got 15 nodes, I'm still going to be able to do that in 4 levels, right? Because here's 7, I can add 8 more and still stay in my height of 4. But when I add that one more after that and get up to 16, then I'm going to have to bump it up to a 5th level. Okay, so what's the function here? If I have n nodes, what's the
2
minimum?
to the power of n? Or
That's exactly right, except it's the opposite, right? If I was saying
log base.
the minimum height was n, how many nodes is that? You could say 2 to the n, right? 2 to the 5. I guess that would actually be technically 2 to the n minus 1. I mean, we're approximating anyway, but you know, 2 to the 1 is 2. Yeah, so it's log n. And don't ask me why I'm using uppercase all of a sudden. Okay, now this is approximate, right? It's actually going to be log to the base 2 of n, what do I want to say here? Log base 2 of n, and then add 1 to it. Anyway, something along those lines, but basically what we're saying here is, yeah, one step ahead of me. Close to that, like, well, we still have to take into, anyway. Yes, roughly speaking, what we care about is that this is a logarithmic function, right? Which is a good thing. That's the reason the binary trees are so huge. It's because we have a structure now where the height of the tree, assuming that it's not too far out of balance, the height of the tree is going to be approximately log n. So when I'm searching for a node, it's going to be very similar to searching for a number in a binary search, right? Each time I look at a number, I can divide the number of remaining possible results by half. So anyway, that was actually a very long conversation to give you a sneak preview on what's coming up with binary search trees. Looks like they did basically the same thing I did, right? Okay, so we've talked about binary trees and binary search trees. What's going to happen next, you should probably be able to predict this by now if you've been doing the reading, is that we're going to actually define the abstract data type. We're going to do it, oh, we get to talk about pre-order and post-order first. Forgot about that. Okay, so this is actually really good stuff. I'm excited to talk about what's coming up next. Remember in our discussion of expressions, we talked about prefix and infix and postfix. This is going to be very closely related to that. If you didn't get that at the time, you're going to want to go back and review that, because we're going to be talking about pre-order, in-order, and post-order traversals of a binary tree. It's going to be very closely related to the different kinds of expressions we talked about back in whatever lesson that was. Okay, sorry to have to be so short today, but something to look forward to on Thursday. We get to talk about these traversals, which are fun, and then we'll start talking about some code. So I will see you all on Thursday.